Hi everyone, in this video we will see together how to use the NanoFrazor to check your samples after the development in a bilayer lift-off process. I will say this is not a very standard use of the NanoFrazor, but in order to see how our bilayer lift-off process works and also how we can use a NanoFrazor to read our surface after the development step, I think it's a good occasion to show you something different. So we saw in the previous videos of this short series about the bilayer liftoff, first of all, how to make samples, and then we prepare some samples, I pattern and did a development, and you can see here some of the results after the development. So we tried to pattern different things with the laser, and we can see that the sum of the squares that we pattern are still visible on the surface after development. And we can also see that the TFPL fields are also visible. Maybe we can try to focus on the surface a little bit more to see if we can see the structures a little bit better. But anyway, I would say this is already a good result in my opinion, because we still see all our structures after the development. What I want to check now is the depth of these structures, because the NanoFrazor can be useful to understand whether we removed all the PMMAMA underlayer or whether there can be still some residues of polymer. It's also possible the etch rate is not high enough or the etching time was not long enough, so we didn't really remove everything. So we can use our reading function. Let's maybe first read a field that we did with a laser, so we can take also this arrow and I place a field here. So we said that we have 30 nanometers of PPA and 100 nanometers of PMMAMA. So I should set the reading depth at maybe 130 to make sure to be able to read the bottom of our structures. In this case, I can also use a fast scan correction because both of the ends of my field are flat. So let's turn it on. And thermal conductance correction can also help because here we removed a lot of material that we may have the silicon exposed. We probably have the silicon exposed, which will change a lot the thermal conductivity between this area and this area. So let's also use the thermal conductance correction. And we can run the process. So I hope to see a step of around 130 nanometers depth. It can be a little bit more, it can be a little bit less. By following the spin coating tables, there is of course a expected thickness of polymer, but there is always a small error. So maybe if there is a difference of few percentage, I don't know, 3-5%, it's still within the range of expected thicknesses after spin coating. So we can already see here that we have a very deep structure. Okay. Seems around 130, 135 nanometers deep. We can also double check with our lines. This seems a little bit deeper than 130, but again, within the expected depth. And I will say this is already quite a good scan. It tells us already that we removed most likely all the PMMAMA that was exposed after the patterning. So I will try to put the sample in an evaporator and perform the evaporation and then do the liftoff. This is what I will say after looking just this cross section and this specific area of the sample. But I still want to check if the features at higher resolution survived and how the TSPL basically was altered after this development. So maybe let's check the wheel. We said that the wheel is a good structure to check also how the isotropic development can start the merging of the feature after we are developing too long or just because the features are too close together. So at some point we should see in this wheel, first of all, let's check the quality, but we should see that as we are getting closer and closer to the center of the wheel, we'll see that the features will start merging. And by measuring this, the area where it merges versus where it doesn't, we should have an idea of the resolution and the density of the feature that we can have. The reading is not that great. We're scratching a little bit on the surface, but the depth is pretty much as expected, and we can already see here that we're starting having some problems. Indeed, we see that the surface is not sharply, these steps are not sharply defined. We start seeing a merging of the features, and here basically we don't have the features that are very visible anymore. So we should be able to transfer from here down or from here right, I mean, depending how you consider. Basically outside this inner circle the liftoff should work, while inside should not work. So by measuring, let's say, this separation, it should give us an idea of the density of the feature we can achieve. And we can also do it now. Maybe it's a little bit sharper separation in this area. So we can check 1 and 2. This is 1 and 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. Basically, this area here should give us an idea of the separation we can achieve, which is around, I would say, 200 nanometers, as expected. Like we expect a separation which is within this range, 200 nanometers. I overedged by 50%. So maybe 250 nanometers, something like that, should be pretty much the minimum feature density that we can achieve with this specific bilayer liftoff sample. Lastly, we can also do a reading of our windows here. We can see that this is a window structure that we said is also a good structure to identify the resolution of the process and the density of the feature that we can achieve. So we can start the reading. In this case, if you see here, I slightly changed the pixels to make it a little bit faster. Maybe I can also put 60 here to make this reading a little bit faster. And what we should see is that after a certain point, after a certain square, the windows are not visible anymore. They start merging, and that's pretty much where our bilayer liftoff has its limit in feature density. So let's check this last field, and then we can close the video. We draw some conclusions. I will not check all the fields that we patterned here. We can also imagine that based on just this reading, we expect similar merging of the features for patterns where the resolution was higher than this distance. But based on our readings, I will say we did a good development. The surface, I mean, the PMMAMA was removed almost entirely. And we can also see the features. We have some problems in reading. We're not using probably an optimal tip, but we can clearly see that here the features are survived. Here there's pretty much when they start merging. So probably this should still work, but for sure here we will not have any liftoff here as well. And here we don't see any lines anymore. They're basically removed. We can see traces of these pieces of polymer that were removed, but still hanging there, basically. And yeah, I think this test already confirms what we were expecting. And here we can see that the resolution or the density is around 250 nanometers, like the separation between features here. So now what we have to do is put our samples in an evaporator, perform an evaporation, and then doing a liftoff. And in these training videos, we will not put the evaporation process as, let's say, step that you will find with the video. So I hope that you have a good evaporator. Usually we do thermal evaporation or E-beam evaporation. Sputter is not as good as evaporation, but should still work. So it's important that also your evaporation process is working well. And what we usually do is also putting maybe some few nanometers of adhesion layer, let's say titanium maybe on gold. It also depends on the metals and substrate that you use. But then we will see together also a short video for the liftoff process, which is going to be, in this case, in acetone or DMSO. Depends also on the materials that are involved in your specific samples, and also depends whether you're using PMMAMA or PMGI. But so far, I will say we're happy with these results, and see you in the next videos of the series. And I hope this helps in understanding a little bit more about the development process, by the liftoff process, but also how to effectively use a NanoFrazor to check your process and to increase the success rates of your process.